Hello everyone, my name is Katheryn Neumann, and I've been working on a regional analysis of Florida power transmission lines under hurricane conditions. The motivation of this study is based on the lack of research on regional analysis for power transmission networks compared to other infrastructure such as buildings or transportation. My study, Combined Hazard and Vulnerability Analysis for Power Transmission Lines, focuses on assessing the susceptibility of these vital assets to wind-related risks, particularly in hurricane-prone regions like Florida. Specifically, I was looking at how wind direction is a vital component of model making, in addition to the commonly used intensity measure, wind speed. Hurricanes are often characterized by wind speed as their intensity measures and several other dimensions of wind speed that are important to different failure modes of towers. These include gust wind speeds and sustained wind speeds at different time intervals. But this study investigates the crucial role that wind direction also plays in determining the structural integrity of transmission towers on a regional scale. Using a regional analysis and catastrophe modeling tool called INCOR and historical data from Hurricane Ian, I analyzed the impact of wind direction on transmission towers. INCOR is a Python-based modeling tool that allows for the use of their database and implementation of their Python library on a cloud server's Jupyter lab. This way of running large amounts of analysis can be done faster, since their platform is built for this kind of highly repetitious running. The wind data of Hurricane Ian I used came from NOAA's Hurricane Database, which records the max sustained wind speeds in relation to the track of the hurricane, recorded every 6 hours. Since this data is quite large in scale, a linear interpolation model was employed to return a more varied max wind speed between the centers of the hurricane and the edges of the polygon. The tower network was created using power line data of Florida and assuming a tower density to place towers every 500 meters. This resulted in approximately 63,000 towers to be considered for failure. Two different fragility curves for tower damage were employed, one which corresponds to wind at a 0-degree angle, and the other for wind at a 30-degree angle. The damage of each tower was assigned using an INCOR function and gives probability of failure for each tower. This damage was visually represented by figures 4 and 5 for each wind direction. The functionality assessment I coded was fed by a Monte Carlo function supplied by INCOR, running 1,000 random configurations of damage based on the damage state probabilities. The functionality of the system was determined to be a function of voltage and length of the lines and is represented mathematically by equation 1. The results of a damage and functionality assessment using INCOR's Python library and database indicate that certain lines are more likely to fail than others in a random sampling of 1,000 damaged line configurations. As seen in the figures, since certain lines had more damage and such lines varied between the two wind directions, wind direction does significantly influence how these towers respond during hurricanes. Additionally, assuming the wind blows uniformly in one direction for all the towers can lead to gross underestimation or overestimation of the network's functionality. The result of this study opened the door for factors like tower age and design to be considered, which could further contribute to vulnerability. By considering these multifaceted elements, research can provide a more comprehensive understanding of the resilience of power transmission lines in the face of hurricanes and tropical storms. Considering tower age and design are often linked to geographic region, and towers of the same line are of the same vulnerability, further research includes correlation studies using probability fields to geographically overlay Florida's tower network. By accurately assessing the vulnerability of transmission lines and incorporating factors like wind direction into hazard assessments, stakeholders can better prioritize mitigation strategies. This means enhancing the resilience of our power systems and minimizing downtime during extreme weather events. This study serves as a crucial step towards safeguarding our power transmission networks. By leveraging engineering expertise and advanced modeling techniques, it offers valuable insights that can help us better prepare for and respond to hurricanes and other natural disasters. And in regions like Florida, where the threat of hurricanes looms large, this research couldn't be more timely or essential. Thank you for your time, and I hope you enjoyed the presentation.